Hello students, in my last lecture we talked about different thermodynamic parameters of an electrochemical cell. In this lecture we will talk about pH, pKa, buffers and corrosion. pH is defined as the negative logarithm of hydrogen ion activity, normally represented as Ah plus, or we can also define it as the decimal logarithm of the reciprocal of hydrogen ion activity, that is Ah plus in a solution. We can write an expression to explain pH as pH is equal to minus log at the base of 10 activity of hydrogen ion concentration, which is also equal to log at the base 10 and 1 by activity of hydrogen ion concentration. Pure water which we use has hydrogen ion concentration is equal to 10 raised to the power minus 7, and therefore its pH is equal to 7, which represents a neutral pH. Acids have a high hydrogen ion concentration and thus they have a low pH value, that is lesser than 7. On the other hand, bases have a low hydrogen ion concentration and thus they have a high pH which is greater than pH 7. If we look at the complete pH scale from 0 to 14, we can see here that pH 7 is a neutral pH. If we go down, the pH becomes acidic, and if we go higher, the pH becomes basic, or we can say that the solution becomes acidic when pH is lesser than 7 and the solution becomes basic when pH is greater than 7. Similarly, we can also determine pOH, which is sometimes used as a measure of the concentration of hydroxide ion, or you can say OH minus, or it also provides information on alkalinity of the solution. pOH values are derived from pH measurements, and the concentration of hydroxide ion in water is related to the concentration of hydrogen ions by a relation OH minus is equal to Kw divided by hydrogen ion concentration, where Kw represents the self ionization constant of water. If we take logarithm in this equation, we can write it as log OH minus is equal to log Kw minus log H plus, and for pOH we write it as minus pOH is equal to pKw plus pH. This gives a relation which is pKw is equal to 14, which is equal to again similar to pH plus pOH, which indicates that the sum of pH and pOH in a solution will always be equal to 14. Thus, for any solution where the pH is known, we can write pH plus pOH is equal to 14, or pOH is equal to 14 minus pH. Now, let us have a look at the table which provides information on different hydrogen ion concentration and their corresponding pH, pOH and OH minus in mole per liter. Say a solution has hydrogen ion concentration as 10 molar, its pH will be minus 1, pOH will be 15, and you can see the sum will be again 14, and OH minus concentration will be 10 raised to the power minus 15. Similarly, the different hydrogen ion concentrations provide us information about pH and pOH, from which we can calculate the value of OH minus. In all the cases, you can see that the sum of pH and pOH is always 14. Now, the question comes, what is pKa? pKa represents difference between ionization and dissociation. Ionization is a process in which ions are formed from neutral compounds, whereas dissociation indicates the separation of the ions of an electrovalent compound as a result of the action of a solvent, which is usually water. For a weak acid which dissociates as follows, Ha is giving hydrogen ions plus A minus, and the extent of such dissociation is controlled by the acid dissociation constant Ka, which can be given as Ka is equal to hydrogen ion concentration multiplied by A minus divided by the concentration of Ha. Now, we can use the well-known Henderson-Hasselbalch relation, which indicates Ka is equal to H plus multiplied by A minus divided by Ha, and taking logarithm of this expression, we can represent it as log Ka is equal to log H plus log A minus log Ha, and we can write now minus pKa will be equal to minus pH plus log A minus divided by Ha. Now, we get an expression where pH is equal to pKa plus log A minus divided by Ha. This equation relates pH and pKa is an extremely useful relation known as Henderson-Hasselbalch relation. According to this relation, pH is equal to pKa of an acid at the point where it is half dissociated. For example, again consider the same relation. Ha is giving H plus and A minus. At the point where H plus is equal to A minus, pH will become equal to pKa. We can also see from the relation pH is equal to pKa plus log A minus divided by Ha, and at the point where H plus is equal to A minus, this relation will become pH is equal to pKa plus log 1. That is because A minus is equal to H plus and the pKa plus 0, and we can write that at this point pH will be equal to pKa. To make it more clear, let us consider a simple question that aspirin, which is a well-known drug, has a pKa of 3.4. Now, for this compound, what will be the ratio of A minus to Ha in blood and in the stomach? The pH of the blood is about 7.4, and in the stomach the pH is more acidic and is close to 1.4. Now, we know the relation pH is equal to pKa plus log A minus divided by Ha. pH is known, it is 7.4 and pKa is 3.4. Then we can write it that 7.4 minus 3.4, which is equal to 4, is equal to log A minus divided by HA. This indicates that the ratio becomes 10 to the power 4 for A minus divided by HA, and similarly for part B, that is in stomach, we can write pH is equal to 1.4, pKa we know 3.4, and we can write 1.4 minus 3.4, which is equal to minus 2, is equal to log A minus divided by HA. This gives 10 raised to the power minus 2, that is 0.01 is the ratio for A minus divided by HA. By using pKa values, we are able to express the strength of an acid, that is its tendency to dissociate with reference to the pH scale. If Ka is large, the pKa will have a low numerical value. For example, hydrochloric acid HCl has a pKa is equal to minus 3. Acetic acid has a pKa which is equal to 4.77. This indicates that acetic acid is a weak acid, whereas hydrochloric acid is a strong acid. A strong acid is the one which is largely or completely dissociated and which therefore has a high Ka value, or we can say a low pKa value. On the other hand, a weak acid is the one that is only slightly dissociated in solution and has a low Ka value, or we can say high pKa value. The next part comes is buffer. A buffer is a solution that can resist pH change upon the addition of an acidic or basic components. It is able to neutralize small amounts of added acid or base, thus maintaining the pH of the solution relatively stable. Buffer solutions have a working pH range and capacity which dictate how much acid or base can be neutralized before pH changes. A buffer is simply a mixture of a weak acid and its conjugate base, or a weak base and its conjugate acid. The use of one or the other will simply depend upon the desired pH when preparing the buffer. We have different types of buffer, particularly acidic buffer, basic buffer, and the next question comes, how buffers work? If we mix a weak acid with its conjugate base, both the acid and base components remain present in the solution. Since a weak acid rarely dissociates in water, likewise the conjugate base A is a weak base, it rarely steals a proton from water, and therefore high concentration of the weak acid or weak base remains in the solution, since they only rarely react with water. Let us see how buffers actually work. Buffers are very likely to react with any added strong base or strong acid. Let us consider here we have a weak acid and weak base. We are adding them in a mixture. If a strong base is added to a buffer, the weak acid will give up its proton and transform the base into water, and itself changes to the conjugate base as follows. The reaction goes, Ha reacts with OH minus, giving A minus and H2O. Since the added OH is consumed by this reaction the pH will change only slightly. This is a representation. We are adding OH minus to HA, which is giving A minus and H2O. When a strong acid is added to a buffer, the weak base will react with the proton from the strong acid to form the weak acid HA as follows. H plus is reacting with A minus giving HA. The hydrogen ions gets absorbed by the A minus instead of reacting with water to form H3O plus, and therefore again the change in pH is very small. This is again a representation. We have HCl here, we are adding A minus, which is giving HA and forming Cl minus. As we can see, over the working range of the buffer, pH changes very little with the addition of acid or base. Once the buffering capacity is exceeded, the rate of pH change quickly jumps. This occurs because the conjugate acid or base has been depleted through neutralization, and this principle implies that a large amount of conjugate acid or base will have a greater buffering capacity. This graph shows the relation between pH and acidic basic relation, that is H3O plus is equal to OH minus. In the beginning, we can see the pH increases and goes up to about pH 5. Then the change in pH can be observed as a slow reaction followed by the conjugate acid is depleted. In the first case, conjugate base is depleted. In the last case, conjugate acid is depleted, and in such a case the buffer range is shown by this green square. Rather, we can call it as rectangle, and the middle of this change represents pKa of the solution. Let us now come to acidic buffer. A buffer solution containing a large amounts of a weak acid and its salt with a strong base is termed as an acid buffer. Such buffer solutions have pH on the acidic side, that is lesser than 7 at 298 K. Example: acetic acid, which is weak organic acid, and a salt containing its conjugate base, the acetate ion such as sodium acetate, acts as acidic buffer. This is the reaction, that is acetate ion is reacting with H3O plus giving acetic acid and water. According to Le Chatelier's principle, addition of a small amount of acid reacts with the acetate ion and decreases the pH of the solution. On the contrary, addition of a small amount of base, the acetic acid will react with it and form acetate ions with water. Hence, the pH remains unchanged. Let us now consider basic buffer. A buffer solution containing relatively large amounts of a weak base and its salt with a strong acid is termed as a basic buffer. Such buffers have pH on the alkaline side, that is pH greater than 7. For example, ammonia, which is NH3, and a salt containing its conjugate base, the ammonium cation, such as ammonium hydroxide, acts as basic buffer. Here the reaction is that NH3, that is ammonia, reacts with water to give NH4 plus ammoniamine and OH minus. Henderson-Hasselbalch equation for buffers. These buffers must be chosen for the appropriate pH range that they are called on to control. The pH range of a buffered solution is given by the Henderson-Hasselbalch equation, which is pH is equal to pKa plus log salt concentration divided by acid concentration. pOH is equal to pKb plus log salt by base. To make it more clear, let us consider a question. What pH do you get when to 0.1 molar acetic acid, that is 4.76 pKa, you add 0.02 molar NaOH? The reaction is, we are taking acetic acid CH3COH, which is reacting with NaOH to give sodium acetate and water. The initial concentration of acetic acid is given as 0.1 and we are adding NaOH with 0.02 molar concentration. Now, in this case, the sodium acetate formed will be 0.02 and again water will be formed with 0.02 molar. Now, since on addition of 0.02 molar NaOH, the acetic acid will react with it and form 0.02 molar acetate ions along with water. Similarly, amount of acid left will be 0.1 minus 0.02. Hence, the pH of the solution will be equal to pKa plus log 0.02 divided by 0.1 minus 0.02, which will be equal to pKa is already given as 4.76 plus log 0.25 and pH will be now 4.76 minus 0.60 is equal to 4.16. There is another question for buffer solution. Let us calculate the pH of a buffer solution containing 0.2 mole of ammonium chloride and 0.1 mole of ammonium hydroxide per liter, where Kb for ammonium hydroxide is given as 1.85 into 10 to the power minus 5. Again, we are using the same equation. pOH is equal to pKb plus log salt concentration divided by base concentration. Now, pKb is equal to minus log Kb, which is again equal to minus log 1.85 into 10 to the power minus 5, which is a given value, and this becomes 4.733. Therefore, pOH will be equal to pKb plus log 0.2 divided by 0.1 and we will get 4.733 plus 0.3010 and the pOH in this case will be equal to 5.034. Now, pH we know is equal to 14 minus pOH and therefore, the pH of the solution will be 14 minus 5.034 is equal to 8.966. We must remember at this stage that for a solution having pH lesser than 7 are acidic and the solutions having pH greater than 7 are basic in nature. Let us now come to corrosion, which is a big problem because rusting, which is spontaneous oxidation, causes damage of billions of dollars every year in the world. Most structural metals have reduction potentials that are less positive than oxygen. For example, if we consider iron, it rapidly oxidizes to give Fe plus 2 and 2 electrons are evolved. the standard electrode potential for this reaction is 0.44 volt. Now, oxygen reacts with water in presence of 4 electrons to give 4 hydroxide ions, and the standard electrode potential for this reaction is 0.40 volt. Now, the iron plus 2, that is Fe plus 2, reacts with oxygen in presence of water to give Fe2O3 and H plus, and this reaction is the main reaction which is responsible for corrosion. Reaction happens in two places. Let us consider a ship's hull where corrosion is a very big problem. Here we can see, say this is water, and above the surface of water oxygen is available. This is the hull of the ship. Now this hull starts acting as anode as well as cathode. The reactions are same. Oxygen reacts with water and 4 electrons giving 4 OH minus, whereas iron 2 plus reacts with 2 OH giving ferric hydroxide, which reacts with oxygen to give 2 Fe2O3 H2O, which is rust, and 2 molecules of water are formed. In anodic region, we can see we have Fe2 plus, whereas in cathodic region OH minus is formed. Now electrons migrate from anodic to cathodic region. Now for preventing corrosion, several steps are possible. First, we can coat, that is the coating, to keep out air and water so that the reaction does not take place. Galvanizing, that is putting a zinc coat on the surface of iron, and in this case it lowers reduction potential, so it is more easily oxidized and iron remains unaffected. Alloying the metals to form oxide coats, and the last one is cathodic protection, that is attaching large pieces of an active metal like magnesium that get oxidized instead of iron. This is an example of preventing the corrosion of iron by cathodic protection, that is sacrificial anode. Here we have coated iron with zinc, which is acting now as anode, giving zinc as zinc ions and 2 electrons, iron which acts as cathode, that is oxygen plus 4H plus 4 electrons giving 2 water. Now you can see electrons are going from zinc to iron, and zinc is converting to Zn plus 2, and in this case this is the water droplet, and iron remains same and no reaction of Fe3 plus or iron metal takes place when it is coated with zinc. This is another example. If we add salt, it speeds up process by increasing conductivity and the rust formation becomes more. This is water droplet, and here iron starts dissolving giving Fe plus 2, which reaches near water surface, and Fe2 plus reacts with oxygen which is available at the surface, 2 molecules of water to give Fe2O3 and 8 protons are formed. Now oxygen which is available at the surface reacts with 2 molecules of water and 4 electrons giving 4 hydroxide ions. Now these electrons and Fe2 plus starts forming rust, which is Fe2O3, which can be seen at the surface of iron. This type of rust you must have seen in iron objects which are during rainy season are exposed to open atmosphere where water or humidity is available, oxygen is available and iron metal is available, and you can see this type of brown rust in your iron objects which are left to air during humid season. Let us now come to applications of cathodic protection. Galvanized steel which is coated with zinc. This type of screws, nuts you can see in the market where zinc is coated. Sacrificial anodes, ship hulls which we already discussed, and subs, that is submarines, free flooding areas. These are some nuts which are coated with zinc. This is an example of Earle Burke destroyer, which is a guided missile destroyer in the United States Navy, and the cathodic protection of this ship helps us to protect it from corrosion. Another example is Los Angeles class submarine, which is nuclear powered fast attack submarine in the service of United States Navy, where cathodic protection helps them in protection from corrosion. In this lecture, we talked about pH and buffers, pKa and corrosion. In the next lecture, we will talk about various types of electrodes which we can use in electrochemistry.